Hi everyone, I'm going to talk you through the first two lectures that we've posted so far on special relativity. I'm not going to go over all the algebra in this video. I'm going to talk you through the big conceptual ideas and how to think about things, which is more important. If you want the algebraic details, check out the solutions posted on Blackboard. All right, let's get started. So the first thing we're going to start with is talking about the postulates of special relativity. So I'll abbreviate that SR. And these are postulates are just assumptions. They're the starting point. And it's kind of different from most of physics, where we start out by thinking about what's the experimental outcome of something and how do we explain it. In special relativity, we actually start with big assumptions about how the world works. And that's because in special relativity, the experimental outcomes are pretty hard to observe. So Einstein took a lot of theoretical work that was happening in the late 1800s and early 1900s and encapsulated all of that into two postulates that he started with to derive the rest of special relativity. After that point, we've done lots of experiments to show that these are actually true, or at least the consequences of them are true. So let's talk about them. The first postulate is all inertial reference frames are equivalent. And an inertial reference frame is a fancy way of saying an unaccelerated observer. It's someone according to whom Newton's first law works, i.e., things are only going to move if they're pushed on by a force. And that's violated, for example, when you slam on the brakes in your car. All the change you have sitting, on the dashboard is going to fly forward. Nothing pushed on it, it just started to move relative to you. That's because you're an accelerated observer in a non-inertial reference frame. So we don't talk about those for special relativity. That's the subject of general relativity. But all the inertial ones, this is every reference frame we've used so far in class. They're all equivalent. It doesn't mean they're all equal to each other. You have different points of view and different ways of describing things in different reference frames, but they're all just as good. And the second postulate is a little special. It says light travels at c, the speed of light, 3 times 10 to the 8 meters per second. Why is light singled out? Why does it have this speed? Hard to say. It comes out of Maxwell's equations for electricity and magnetism, and it was a subject of confusion for a long time. But we're going to take it as a given and see what the consequences are. So in the first lecture on special relativity, we studied a thought experiment called the light clock. And Einstein was very fond of thought experiments because you could come up with a system that was maybe impractical to really build, but told you something really deep about what was happening. And the light clock is one example. I don't know of anybody who actually goes and builds a light clock for the purpose of measuring time, but we can imagine it. It's two mirrors separated by a distance h, and the clock ticks every time light bounces back and forth between the mirrors. And so you can calculate that out. You can say, well, the light has to travel a distance 2h, and it's moving at c, according to postulate 2. And so the time that it takes, delta t, to tick is 2h divided by c. Pretty straightforward. But what happens next? Let's look at it from a different frame of reference. And importantly, it's the same clock, it's the same light, it's the same mirrors, just according to somebody else. What about this little stick figure moving to the left is going to, from their point of view, see the light clock moving to the right. They're going to see that light form this triangular pattern. It's going to bounce from the bottom to the top to the bottom again. But as the clock moves to the right, from their point of view, from their frame of reference, it traces out this triangle. And you can see just from the picture that triangle is a longer path for the light to follow. And so the clock from the right frame of reference is going to take longer to tick. We call that time delta t prime, and it's got to be bigger than delta t, and the proportionality factor is called gamma, lowercase Greek letter gamma. And the formula for gamma is a little messy. You can derive it with algebra by calculating the size of that triangle. And the formula is it's 1 over the square root of 1 minus v squared divided by c squared. So the speed of light is special. And the bigger the speed of the moving clock compared to the speed of light, the more dramatic this slowing down of the light clock is. But that's just one clock that we made up. How do we know that it's true for all clocks? Um, and so let's do another experiment, another thought experiment. Let's imagine that I have two different types of clocks. I have a normal mechanical clock. Maybe it's driven by a pendulum or a spring or an electronic circuit or a quartz crystal or whatever. It doesn't matter. Any clock, regular old clock next to a light clock, and I calibrate those to have an equal rate of ticking when they're at rest. So I bring them both to my lab and I tweak them until they tick at the same rate. And then I load them up into a spaceship and blast them off at speed v, which is pretty high. And so, according to the last slide, that light clock is going to tick slower, but maybe the other clock doesn't. Maybe it doesn't slow down the same way that the light clock does. It doesn't seem like there's anything wrong with that. We could say that those different rates, those clocks have different rates when they're moving. Maybe that's okay. Here's where the contradiction is in that. Imagine now there's a different observer on the spaceship. Our astronaut thinks to himself, wait a second, these clocks, which are supposed to tick at the same rate when they're at rest with respect to me. They're not moving anywhere, but the light clock is ticking slower. Therefore, that astronaut can conclude that they are moving, even though their point of view that they're at rest in that rocket ship should be just as good. That's something that you can't conclude according to the first postulate of relativity. It's not so much the second postulate that's powerful, it's the first postulate that all these frames of reference, including the astronaut's frame of reference, are just as good. So the astronaut should be able to conclude that he's moving. That's supposed to be impossible. So if the astronaut can't conclude that, then the clocks can't tick at different rates. And if no conceivable clock can act differently than the light clock, it's not really something about clocks that we're talking about, it's something about time. And that's why we call this time dilation. It's the passage of time itself that moves slower for moving objects. And I shouldn't say move slower for moving objects, because from their reference frame, time flows normally. Their reference frame is just as good. But when we observe other objects moving at high speed, we observe their time to be slower than our time. And that's the nature of time dilation. It's relative, hence special relativity. A couple other important effects come up in lecture 24. Length contraction is a consequence of time dilation. They're sort of equal and opposite types of effects. And the result is that if you have something like a moving ruler, its length when it's moving is actually shorter than its length when it's at rest. And of course, whether it's moving or at rest is relative. What frame of reference are you in? Those objects have different lengths in different frames of reference, but all those frames of reference are equally good. It applies to the sizes of objects, but it also applies to like the distance between objects. And so there's an example about Han Solo in the notes. The length of the Kessel Run is actually shorter from Han Solo's perspective because it's been length contracted, and that's why he can complete it in less time according to him, but not according to a spectator. The frames of reference result in different times and different lengths, but everything is consistent between the two. One thing to note is that length contraction is only in the direction of motion, and so if you take a basketball and you throw it at half the speed of light, it's going to appear squished, but only in one direction. It's going to look like a pancake. The last thing to talk about that came up in lecture 24 is the relativity of simultaneity, and that's a mouthful. And that's basically saying, let's suppose that we have two light bulbs that flash at the same time. We'll label the left one A and the right one B. Well, what's at the same time mean? It means that somebody standing there gets hit by the light at the same time. And they would conclude then that those two bulbs flashed at the same time. They were simultaneous. But as you'll show in lecture 24, somebody moving past those bulbs is going to compute. They're going to see the light at the same time, but by working backwards to find out when the bulbs flash, they're going to find that bulb B flashed first. And somebody moving in the opposite direction would do the same thing, and they would find that bulb A flashed first. And that's really weird. The fact that things that we think happen at the same time may not happen at the same time according to somebody else is really kind of troubling. Especially the fact that the order of those events can change. Which one flashed first, A or B? It's not a question that you can answer in special relativity. Um, and in a couple more lectures, we'll have an answer for when we can say that one thing happened before another and when we can't. For now, it's supposed to be a little bit troubling. So that's all I have for this video. Um, Let me know if you have any questions. Thanks.